In this video, we're going to take a more detailed look at current electricity and what makes it different than static electricity. From the introductory video, you'll remember that the main difference is that the electrons in current electricity are constantly moving, whereas the electrons in a static electrical charge are trapped within a single location until they're able to be discharged back into the ground. So what exactly allows current electricity to form, and why can't this happen in a static electrical situation? Well, if we take a look at the structure of electrical wires, which basically every electrical current needs, we can understand from their structure why currents can form. So we see that the inside of electrical wires, and again, this is where the electrons are actually moving, we can see that the inside of these wires are made of metal. More specifically, they're made of a metal called copper. Now, copper is very useful for electricians and electrical engineers because copper is what's called a very good conductor of electricity. This means that electrons that are moving in a current can move relatively easily and relatively quickly through metals such as copper in particular. Copper is not just widely available on Earth, but it also makes a very good conductor, which is why we use it in electrical wires. Now, most people that know even a little bit about electrical wires understand why the wires have to be covered by plastic or rubber, and if you've ever touched a metal wire that has been plugged into something, you're going to get a nasty shock because the electrons that make up the electrical current can escape and go into you. So that's why we need the plastic or rubber covering. Their job is to prevent the electrical charge, the movement of electrons, from escaping from the wire. So unlike with the metal that copper wires are made of, electrons have a lot of difficulty with passing through the plastic or rubber covering, and therefore plastic or rubber is what is called an insulator, meaning it's a material that prevents the flow of electricity. Now, when we arrange electrical wires in a very specific orientation, and when we add a number of other components, such as this setup here, we get what is called a circuit. And the circuit is the fundamental unit of all current electricity and requires a number of different components to function, which we can go through one by one. So remember that electrons are part of atoms, and we can't just make atoms out of nowhere. Electrons need to come from somewhere, and most people will understand that if you want to power an electrical device, you need some sort of power supply, such as the batteries that we have here. So the job of batteries within an electrical circuit, says battery here, but we actually have 3 batteries here, is to supply the electrons. So if we look at this circuit here, we can see that these arrows are moving in specific directions. So here, the electrons will leave the battery and flow toward the light bulb in a clockwise fashion. So here we can see at this end of the battery, there is a plus sign indicating that we have the positively charged side of the battery here, and we can tell that this is positive because we can see that the electrons are moving away from the battery, meaning that this side is losing electrons, and that's what gives it the positive charge. This side of the battery is technically what we call the anode, and when the when the electrons leave this side of the battery, this creates what we call a current, the constantly moving flow of electrons from one end of the battery to the other. So current, which we measure with, or which we record with the variable I. Why do we use I for current? I genuinely don't know. If you wanted to actually measure the rate of electron movement, we use a unit called amperes, although most people will simply refer to these as amps. So the higher the number of amps, the faster the electrons are moving through the circuit, and amps we measure with the short form capital A, like this. Now we can also describe how much power we can get out of batteries by measuring something that we call electrical potential. So this is a little bit oversimplified, but basically the higher the electrical potential of a battery is, that means the more power we have the capability of generating using that battery, and the variable that we use to measure this is what we call voltage, the symbol of which is V. And again, the short form for the unit that we use for measuring voltage is the unit volts. So the higher the number of volts that batteries can use, the more power we can get out of a battery. Now, there is one more variable that we need to consider, and that is the concept of resistance. Now, as the electrons are moving, the electrons are not going to move completely unblocked. They need to move through metal, and every time they go through anything that isn't an electrical wire, they are going to encounter resistance. So resistance basically measures how much the current is slowed down by anything else that is in the circuit. So along with resistance, we can describe any device within the circuit that slows down the current or slows down the flow of electrons is what we call a resistor. So here, this circuit would be representative of one that we find in a computer or on some sort of motherboard, because this resistor here is a transistor. This is a component in digital circuits. So this would be an example of a resistor, and this light bulb, which would also slow down the flow of electrons as it passes through it, would be another example of a resistor. So we can measure resistance using the measurement of what's called an ohm. So the greater the number of ohms, the more resistance the current is meeting, and the slower the electrons are going to move. The symbol that we use to measure ohms is a Greek letter that looks like this. This is the Greek letter omega, so omega is for ohms. Now, because the purpose of this circuit is to power this light here, we don't just describe this light as any ordinary resistor. This is what we call the load. So the load is any device that is connected to a circuit that requires electrical power in order to use. So the flow of electrons in this circuit is actually what we use in order to power this light bulb here, and this is why we refer to it as the load. This is the purpose behind this electrical circuit. Now, obviously, if this light bulb were in a room that you're in, you don't want this light bulb to be on all the time because it's easier to fall asleep when you're in darkness, and you don't want to waste electricity, which means that many circuits will also come with a switch that we see here. Now, the technical name for a switch is what we call a circuit breaker, and we will see why. So again, the job of the switch is to control whether the electrons within the current are able to move through the complete circuit or whether they are not able to. So right now this switch is on because we see that this light is on, which means that this circuit is connected. But if we were to flip this switch, basically what this switch would do is it would move this part of the electrical wire down and therefore break the circuit. Now, if the circuit is broken, the electrons can't move from one end of the battery to the next, which means that we don't have a full current through the circuit, and our light bulb will no longer work. And this is why the term circuit breaker is the technical term for any switch that we have. Now, after we've made it past the switch, we are going to end up at the opposite end of the battery, and we can see that there is a negative sign here. So this is the negatively charged side of the battery, and after electrons move all the way through the circuit, through any resistor that we have, the electrons are going to re-enter the battery and the circuit begins once again. So again, this location is the negatively charged end of the background, because this is where the electrons are moving back towards the battery, meaning that we're going to get negative charge building up here, and the name for this end of the battery is what we call the cathode. In the next video, we're going to look at a notation system that we can use in order to represent circuits so that we don't need to draw out batteries and specific resistors, specific loads, and a circuit breaker. We are going to learn the shorthanded notation system that electricians and electrical engineers use in order to quickly understand and read how a circuit works.